Hi, today we will go into chapter 16, halogen derivative. We will go into detail for halogenoalkane to describe SN1, SN2 mechanism of nucleophilic substitution. So we will go for primary halogenoalkane for SN2 and also tertiary halogenoalkane for SN1. So some of the secondary halogenoalkane will go for SN2 and some will go for SN1. It is always depending on its structure. So for halogenoalkane to go, where it is actually an alkyl group bonded to halogen from group 17. So we can have fluorine that bonded to the alkyl group, chlorine, bromine, or iodine. So if it is a fluorine that bonded to alkyl group, so we will call it as fluoroalkane. Chlorine, it will be chloroalkane. Bromine, it will be bromoalkane. And lastly, we have iodine, where we call it as iodoalkane. So we can group halogenoalkane into 3 different groups, where the very first one we have primary halogenoalkane. So primary halogenoalkane, it's for where the C that bonded to the halogen, it is bonded to 1R and 2H. Okay, what is R? So R, actually it's alkyl group. So where it is alkane as a branch. So it is a carbon chain. So example, we can have CH3. We can even have longer CH3, CH2, CH2, or longer to go. So now here we have primary. We must mainly focus on the carbon that bonded to halogen. So if it is bonded to 1R and 2H, it would be primary halogenoalkane. So what if the C that bonded to the halogen is bonded to 2R and 1H? So it would be secondary halogenoalkane. And lastly, we have where the C that bonded to halogen is bonded to 3R. Then it would be tertiary halogenoalkane. So we need to classify them to move into detail into the mechanism of its reaction. So here we have example of a halogenoalkane. So we have to focus on the longest carbon chain. Here it has 2 carbons. So it will be a bromine that bonded to a carbon chain with 2 carbon. So how can we name it is that we can name it as bromo for the bromine and ethane for a 2 carbon chain. So it is bromoethane. So next to go, we have to go into the reaction of halogenoalkane. So where we have here the C-Br bond, it's a polar bond because bromine, it's more electronegative than carbon. So the electrons of this C-Br bond will tend to move more to Br, means the Br is more electronegative. The tendency for it to attract electrons toward itself is higher than carbon. So therefore, carbon will have delta positive. So this bond is a polar bond. And also, the carbon here is a saturated carbon. So it could only undergo substitution reaction, but not addition. So we could actually have a nucleophile to substitute the Br. So this is how halogenoalkane undergo nucleophilic substitution reaction. So now we will go into detail for the mechanism of nucleophilic substitution. So where we have 2 three different kinds of reaction under nucleophilic substitution, so where they have different nucleophile to go. So first of all, we have OH as the nucleophile. So we have OH minus from the NaOH to be the nucleophile. And next, there will be Cn minus from NaCN or KCN as the nucleophile. And lastly, we have ammonia to have the nucleophile. So we will make use of this reaction, which is hydrolysis of halogenoalkane, to move into detail for the mechanism. So where we have OH minus as the nucleophile. So the very first one, we will move into SN1. So SN1, it's for tertiary halogenoalkane. So where tertiary halogenoalkane will be the C that bonded to the halogen, as in here we have chlorine. It is bonded to 3 R group, where we have CH3, the methyl group as the R group here. So it is a tertiary halogenoalkane. So where in this case, we will have a polar bond for the CCl bond. So we have delta positive and delta negative. So the very first step in this reaction, the CCl bond will be broken. So the electrons will move to the Cl, and Cl will leave as Cl minus, and we have a positive charge for the carbon. And this is the intermediate. And we name this intermediate as carbocation. So the second step in this reaction, we will have the nucleophile. So where we have the OH minus with its lone pair. So move the lone pair electrons into the C positive, and they will form a bond. And this is the final product where we have an alcohol. So the very first step of the reaction will be bond breaking. And the second step of the reaction, it will be bond forming. So therefore, bond breaking is harder than bond forming. So the first step will be a slow step, and the second step will be a fast step. So this is SN1 for tertiary halogenoalkane. So next to go, we will have SN2. So it is mainly for primary halogenoalkane, but there will be some of the secondary halogenoalkane to undergo SN2 as well. So it is always depends on the structure of the secondary halogenoalkane. So let's make this primary halogenoalkane to be the example. So where we have the carbon that bonded to Cl, it is only bonded to one R group and 2 H. So we have the methyl group here to be the R group. So the very first step in this mechanism, there will be no breaking of the CCl bond. It is because if the CCl bond is broken, the halogenoalkane that form will be a primary carbocation, where primary carbocation is not stable. So it will never form as an intermediate. So what happened here is that there will be OH minus, which is the nucleophile. So it will give the lone pair to the C with delta positive, and this is how the bond will be formed. And next to go, at the same time, there will be bond breaking. So this process go together at the same time. So this is where we have the bond forming and also the bond breaking. So this will give us a transition state. So where this transition state, it don't really exist because everything occur in a very fast step. So the bond forming and the bond breaking occur at the same time. So this transition state will have a negative charge. It's because this is neutral and this is negative. So overall, we will get a -1. And once there is bond forming and there's bond breaking, so Cl- will be the leaving group, and there's bond forming between the OH- and the carbon. So we will get a product which is an alcohol. So if we would like to go into detail, so we will see the first step will be a slow step. We need a longer time for the nucleophile to be approached. Once it is approached, and the forming and the breaking will be very fast. So therefore, we will have the first step as a slow step and the second step as a fast step. So that's all for SN1 and SN2 mechanism for nucleophilic substitution of halogenoalkane.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.